Welcome to this lesson on condensation polymers. Condensation polymers are a major class of synthetic and natural polymers formed through a unique reaction mechanism. Unlike addition polymers, condensation polymers are created when monomers join together while simultaneously eliminating a small molecule, typically water. This water removal is the signature characteristic that gives condensation polymers their name. Understanding this process is essential for grasping how materials like nylon, polyester, and even biological proteins are formed. Condensation polymerization is a reaction where monomers join together by eliminating a small molecule, typically water. Each time two monomers form a bond, one molecule of water is released as a byproduct. This is fundamentally different from addition polymerization, where monomers simply add to each other without losing any atoms. The key concept to remember is that for every new bond formed in the polymer chain, one water molecule is eliminated. This repetitive bond formation and water elimination continues, building long polymer chains. To understand condensation polymerization better, let's compare it with addition polymerization. In addition polymerization, monomers add together without any loss of atoms. The entire monomer becomes part of the polymer chain. However, in condensation polymerization, a small molecule is eliminated during the bonding process. This eliminated molecule is commonly water, but it can also be hydrogen chloride or other small molecules. The key difference between these two types is byproduct formation. Addition polymerization produces no byproducts, while condensation polymerization always generates small molecule byproducts. For condensation polymerization to occur, each monomer must have at least two functional groups. We call these difunctional or polyfunctional monomers. This requirement is crucial because each functional group can form a bond with another monomer. If a monomer had only one functional group, it could bond only once and would terminate the chain. But with two or more functional groups, the monomer can bond on both ends, allowing the polymer chain to grow continuously. This difunctional nature enables the formation of long, continuous polymer chains. The classic example of condensation polymerization is the formation of nylon 6,6. This polymer is created from two monomers, hexamethylnediamine, which contains two amine groups, and adipic acid, which contains two carboxylic acid groups. When these two monomers react together, they form nylon 6,6 polymer while releasing water molecules. The name nylon 6,6 comes from the fact that both monomers contain 6 carbon atoms in their chains. This reaction demonstrates the perfect example of condensation polymerization in action. Let's look at the chemical equation for nylon 6,6 formation. The amine group from hexamethylnediamine reacts with the carboxylic acid group from adipic acid. Hexamethylnediamine has the formula H2N-CH2 6 times NH2, while adipic acid is HOOC-CH2 4 times COOH. When they react, water is eliminated, and an amide linkage forms. The resulting polymer has the repeating unit NH-CH2 6 times NH-CO-CH2 4 times CO, enclosed in brackets with subscript N. For every repeating unit formed, one water molecule is produced, which is why we see NH2O as the byproduct. Beyond nylon, there are many other important condensation polymers. Polyester is formed when a diol, a molecule with two alcohol groups, reacts with a dicarboxylic acid. This creates the familiar polyester fabric used in clothing. Kevlar is an aromatic polyamide known for its incredible strength and is used in bulletproof vests. Interestingly, nature also uses condensation polymerization. Proteins are condensation polymers formed when amino acids link together through peptide bonds, with water being eliminated at each connection. This shows that condensation polymerization is not just a laboratory process, but also a fundamental biological mechanism. Let's summarize the essential points about condensation polymers. First, two functional groups per monomer are needed to allow chain formation and growth. Second, a small molecule, typically water, is eliminated during the bonding process. This water elimination is the signature characteristic of condensation polymerization. Third, this process creates materials with unique properties that are invaluable in both synthetic materials and biological systems. Remember, whenever you see water being removed during polymer formation, you're witnessing condensation polymerization. This fundamental process is responsible for creating some of the most important materials in our world, from synthetic fibers to the proteins in our bodies.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.